this chapter is very important from school point of view, from JEE mains and JEE advanced point of view. A lot of questions are asked each year from this chapter. I would recommend you to learn the value of h upon 4 pi to save time in exam, and the value of h upon 4 pi is this shortcut. Then we can get the answer very quickly. Hello everyone, welcome to ATP STEM education. I am Apurv and today we will study about atomic structure chapter. This chapter is very important from school point of view, from JEE mains and JEE advanced point of view. A lot of questions are asked each year from this chapter. So let's do a quick revision of this chapter in which I will be covering all the concepts and all the formulas. So let's begin. The first concept that we have to study about in this chapter is Planck's quantum theory. So Planck said that energy is emitted and absorbed in the form of small packets of energy. He named these packets of energy quanta, and he further gave a formula to calculate energy of each quanta. Energy of each quanta is equal to hc by lambda. The traditional value of h is 6.626 into 10 to the power minus 34. The traditional value of c, speed of light, is 3 into 10 to the power 8 meters per second, and lambda is the wavelength which we have to put in meters if we are using traditional values. But in competitive exams, you will not have this much time to put the traditional values as they are very big. So I would recommend you to use the shortcut value. So the shortcut value of hc is 1240. The only thing which you have to keep in mind that when you use this shortcut, wavelength should be in nanometers. If it is not in nanometers, please convert it into nanometers. And the answer will come in electron volts. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, and 1 nanometer is equal to 10 to the power minus 9 meter. Let's move ahead to the next concept. Before doing that, please keep one thing in mind. Quanta of light was called photon by him. Alright, let's move ahead. See, speed of light is equal to wavelength multiplied by frequency of light. So c is the speed of light, v is the frequency, it's also called nu, and lambda is wavelength. And wave number is equal to 1 upon wavelength. With that, let's move to Bohr's atomic theory. So Bohr said only those orbitals are allowed in which angular momentum of electrons are quantized. That means mvr is equal to nh upon 2 pi. If an orbital is fulfilling this particular equation, then only that orbital will exist, otherwise the orbital will not exist. Now from this particular formulas, a lot of other formulas can be derived. The derivation of those formulas are not important from either school point of view or from competitive examination point of view, so we will skip the derivation and we'll directly go on to the formulas. So the radius of any shell can be calculated by this formula, which is equal to 0.53 into n square by z, where n is the shell number, z is the atomic number. We can use this formula to calculate radius of any shell. This formula will give the value of radius in angstrom. 1 angstrom is equal to 10 to the power minus 10 meters. After that, let's talk about velocity. The formula of velocity of any electron is 2.18 into 10 to the power 6 into z by n meters per second, where z is the atomic number and n is the shell number. In this formula, the answer will come out to be in meters per second. Now we can calculate total energy in 2 units. Total energy can be calculated in joules also. Total energy can be calculated in electron volts also. So total energy in joules is minus 2.18 into 10 to the power minus 18 into z square by n square joules. This is the total energy in joules. But if you want to calculate total energy in electron volt, then the formula becomes this, minus 13.6 into z square by n square electron volt. This is the formula of total energy. Now if we want to calculate kinetic energy of electron, we can use this formula. Kinetic energy is equal to minus of total energy. And if we want to calculate potential energy is equal to twice of total energy, and then we can also calculate potential energy of the electron. Please remember, while applying these formulas, one point is very important. It is valid for only those species which just have one electrons. For example, hydrogen, helium plus, lithium 2 plus, so on and so forth. With that, let's move on to hydrogen spectrum. So today we will be discussing about emission spectrum. That is the most important out of the two spectrums, emission and absorption spectrum. So in emission spectrum, what happens is electron jumps from a higher shell to a lower shell. As you can see in this diagram, all these lines, the transition of electron is from higher shells to lower shells. So when electron jumps from a higher shell to a lower shell, it emits energy. It emits energy in the form of photons. If we allow those photons to fall on a screen, we get emission spectrum. So in hydrogen atom, if electron jumps from any shell to the first shell, it's called Lyman series. If electron jumps from any shell to second shell, it's called Balmer series. If electron jumps from any shell to third shell, it's called Paschen series. If electron jumps from any shell to the fourth shell, it's called bracket, and from any shell to fifth shell, it's called p-fund. And one thing to keep in mind is all the photons which are emitted in Lyman series, they are ultraviolet photons. All the photons which are emitted in Balmer series, they are visible region photons. All the photons of Paschen, bracket and p-fund are infrared photons. Now when electron jumps from higher shell to a lower shell, if we are asked to calculate the wavelength of that photon, then we can use this formula. 1 by lambda equals to Rydberg constant into z square into 1 by n1 square minus 1 by n2 square. So in this formula, the value of Rydberg constant, all of us should remember the shortcut value of Rydberg's constant. So when you will reciprocate this formula, you will have to reciprocate it in order to calculate wavelength. After putting n1 and n2 and z square, z is the atomic number. After putting n1, n2 and z, you will have to reciprocate the value to get the value of wavelength. Please remember that n1 is the lower shell and n2 is the higher shell. For example, in this transition, the electron is jumping from second shell to the first shell. So n1 will be the first shell, n2 will be the second shell. We can put the values of n1 and n2 here to get this particular wavelength if we want to. Also, one very important and very popular question from this topic is number of spectral lines emitted. So we can calculate the number of spectral lines emitted by using the formula n2 minus n1, n2 minus n1 plus 1 by 2. So n2 again is the higher shell, n1 is the lower shell. Let's say electron is going from 3 to ultimately 1. So the number of spectral lines that will be emitted is 3 minus 1 multiplied by 3 minus 1 plus 1 divided by 2. Another type of question which they can ask from this topic is how many of these spectral lines are in Lyman series, how many of them are in Balmer series. Or another way of asking can be how many are ultraviolet photons, how many are visible region lines. So for that, again we will use shortcut values. Now the traditional way is to draw all the lines and then to manually count which one is falling to the second shell, which one is falling to the first shell. To calculate for visible, we count how many lines are falling on the second shell. To calculate for infrared, we basically try to find how many lines are falling on third or fourth shell depending upon the question, right? But if we use this method, this shortcut, then we can get the answer very quickly. Number of spectral lines in Lyman series is n2 minus 1, that's it. For example, electron is in the 7th shell. How many spectral lines will be in the Lyman series if electron is ultimately falling to the first shell? So spectral lines in Lyman series will be 7 minus 1, which is 6. If electron is in the 7th shell, how many spectral lines will be in Balmer series? Or how many spectral lines will be visible? So that will be 7 minus 2, that is 5. I hope this is clear with all. So With this, we are done with the topic of spectrum. We are done with all possible questions of emission spectrum, all possible concepts of emission spectrum we are done with. Now let's move ahead to de Broglie wavelength. So de Broglie said that just like photons have a dual nature, all types of matters must also have dual nature. And he even gave the formula of wavelength to calculate wavelength of matter. And that formula was lambda equals to h upon mv, where h is Planck's constant, m is mass of the object whose wavelength we are calculating, v is the velocity of the object whose wavelength we are calculating. And if we apply the formula of kinetic energy equals to half mv square, and then we substitute the value of mv here, we will get another formula of wavelength that is equal to h upon root of 2 mke. I'll attach this derivation in the description of the video. So if you are interested in it, please do watch the description box and look at the derivation from there. Another formula of de Broglie wavelength is equal to this h upon root of 2 mq into v. This is because kinetic energy can be calculated by this formula q into v, where q is the charge of the object, v is the potential which is being applied on the object. So using these formulas we can calculate de Broglie wavelength of any matter which is moving. Now let's move ahead to Heisenberg's uncertainty principle. So Heisenberg said that it is impossible to simultaneously determine the momentum and position of an object accurately. So he even gave a formula for this, and the formula is this: uncertainty in position multiplied by uncertainty in momentum is greater than or equal to h upon 4 pi. While solving questions, we will be using equal to get the answers. Again, in this h upon 4 pi, I would recommend you to learn the value of h upon 4 pi to save time in exam, and the value of h upon 4 pi is this. Learn this value, this will save a lot of your time in exam, and you will be able to quickly calculate the answer using this value. Let's move ahead to photoelectric effect. So in photoelectric effect, what do? We take a piece of metal and we give a photon, we strike a photon to this piece of metal, and if the photon has sufficient energy, it results in emission of an electron. This electron is called photoelectron, and this phenomena is called photoelectric effect. Any numerical which comes on photoelectric effect can be solved using this formula, where this TE stands for the total energy of the incoming photon, phi is the work function of this metal, work function is the minimum energy needed by the incoming photon to remove the electron. Kinetic energy max is the maximum kinetic energy of the emitted electron. With this, we are done with photoelectric effect. Let's move on to the quantum numbers, the last topic of this chapter. So quantum numbers are of 4 types. The first quantum number is principal quantum number. Principal quantum number gives us the shell number. First shell, when n is 1, when n is 2, it is the second shell, when n is 3, it is the third shell. So number of orbitals in any shell can be calculated by the formula n square. For example, in first shell, there are 1 square, only 1 orbital. In the second shell, there are 2 squares, so there are 4 orbitals. Similarly, we can calculate number of orbitals in each shell using this formula, and maximum number of electrons in each shell can be calculated by this formula 2n square. 2n square is the maximum number of electrons which can come in each shell. With this, we are done with principal quantum number. Let's move on to the azimuthal quantum number. Azimuthal quantum number gives us the value of subshell. Azimuthal quantum number is represented by L, and its value lies from 0 to n minus 1. For example, if the value of n is 2, then the value of L will be 0 and 1. If the value of n is 3, the value of L will be 0, 1 and 2. And each value of L represents a subshell. 0 value of L represents S subshell, 1 value of L represents P subshell, 2 value of L represents D subshell and 3 value of L represents F subshell. After this, let's talk about magnetic quantum number. Magnetic quantum number is represented by M. Magnetic quantum number is concerned with how many orbitals are there in each subshell. So inside subshell there are orbitals, and magnetic quantum number tells us about those orbitals. And the value of magnetic quantum number lies from minus L to plus L including 0. For example, if L is 1, then the value of M will be minus 1, 0 and plus 1. And each value of M represents an orbital. That is why P subshell has 3 orbitals. Let's move ahead to the next quantum number, which is spin quantum number. So spin quantum number can have only 2 values, plus half and minus half. Each value corresponds to a spin of the electron. An electron can spin either in clockwise direction or in anti-clockwise direction. So if clockwise is assigned plus half spin quantum number, anti-clockwise will be assigned minus half quantum number and vice versa. So with this, guys, we are done with all the major concepts of this chapter. I hope you understood everything. That's it for this video from my end, guys. I'll see you in next videos. If you like this video, don't forget to like and subscribe the channel and stay tuned for more videos. Thank you.